Relevant to the problem with the plat, one of the very first problems we looked at. And just to, we have a plat, might look something like this, and that represents the shape of a lot that we say is 3.06 acres. And the problem as posed was, I cut this out of a piece of paper, gave everybody one, gave them rulers, and asked them to take measurements, whatever is necessary, in order to figure out how many feet each of these four sides would be. Okay? And people started by, fairly straightforward. They started by figuring out the area. And what everybody did, everybody got off on a process of dividing this into two triangles and calculating the areas of the triangles. And everybody calculated the area by base times height, or base times altitude, without really stopping to think that altitude is measured perpendicular to base. Now, in the case of these plats, which had, this would be a fairly typical shape, these angles here at the corners weren't that much different than 90 degrees. And at 90 degrees, of course, we would have had a base and an altitude, okay? But there's some error by the fact that these are not measured at 90 degrees. The altitude of this triangle is, for example, here, I think. Bad angle with the board, so I'm not sure I've made a good perpendicular. The altitude of this triangle is actually out here somewhere. Okay, and that's probably not drawn very well either, but we understand that. So there's some discrepancy between the length of a side and an altitude. Not a huge discrepancy, though. You can get a pretty good approximation. You get a pretty good result by just doing what everybody did. Now, had the angles here been bigger, there would have been a lot more error involved in the approximation. However, we're trying to make this approximation as good as possible. Now, other difficulties arose later. Once you get the area of this in square centimeters, how does that relate to acres, and how does that give you the information you need to figure out the length of a side? So there are hang-ups in the problem. It's a good problem. And people should, theoretically, bright people, having had a good geometry course, should be able to think through this, if the course is able to teach anything about thinking and problem solving. Again, thinking and problem solving are not the highest priorities on an SOL test, although they, as I say, the tests are getting somewhat better. So I'm not sure that people were completely prepared to tackle a problem of this nature, but one of the goals of the course is to stretch people, so that's what we did. Anyhow, relevant to the uncertainties that are invoked by, or that result from making that mistake in calculating the area of a triangle, how might we correct that? Now, another thing, of course, that we did was we learned to do some eyeball estimates. So now I've got four triangles up here, and what I want to do is I asked everybody to estimate the altitude of each triangle and the angle. Okay, the altitude, the angle of the triangle, the angle of between this, which we'll call the base, and the marked side. Base is always going to be at the bottom here. We could use any side for the base, but I specified we'll use these sides for the base. We estimate the angle, and I wanted people to estimate the altitude as a proportion of the length of the marked side. So, and then we created a graph of the angle, the ratio versus the angle. So people estimated the first angle to be 120 degrees, and the ratio between the length of this side and the length of an altitude to be 0.75. It's a bit of an underestimate, but that's okay. We're just trying to get a picture and get the problem in our heads by doing some estimates. Okay, so the second triangle, the estimate was the angle's 100 degrees and it's 84%. Again, I think that's a little bit low, but that's okay. Okay, this triangle, well, if that's 100 degrees, is getting close to 90, so the estimate was 95 degrees, and the ratio was estimated to be 0.93. That the altitude is about 93% the length of this side. And then this one, people thought it looked like a 90-degree angle. That was my intent, so I'm glad that I drew it well enough that people could at least conjecture that ratio. And what's the ratio? People were hesitant. Finally, somebody said, well, it looks like 1. And I'd already said it's going to be a really simple answer, and that somebody ventured that, but I think everybody was thinking it. So the ratio is 1. And then we plot the corresponding points on a graph, and we get something that kind of does this. That's not accurate, but it gets the problem in our heads, and then we go to a circle. I didn't specify that the radius of the circle was 1. I just had the circle. And I said, okay, I'm going to divide this 90 degrees into approximately equal angles. And of course, those angles would be 18, 36, 54, 72, and 90 degrees. And I'm going to look at what we would think of as an altitude, okay, this distance here. And we draw some dotted lines across here, indicating those distances. And we mark off a scale here so that we can mark the corresponding points on the graph. And these points in the graph would correspond to what we would have if we had started with a small angle, went up to larger, larger, larger. Because, well, we could put a triangle around this. I'm not going to get too specific about that. But then somebody said something, well, that's a unit circle. One of the students has had a trig course already. So yeah, we put a 1 here and a 1 here. And we also extend the graph. We allow the angles to continue around the circle. So if we continue around here, well, if we go by the same angles, we could just extend the same lines here and get points at the same height but coming down rather than up. And that would make our curve symmetric about the 90-degree point. I don't know that I did a real good job of drawing it that way, but that's the way it would look. And then when we go into the third and fourth quadrants, the graph would go down here. I asked, what does that graph look like? What's a name we would use to refer to that graph? And people said, it's a sine curve. And that's exactly what it is. And then one of the students commented and said, well, you just summarized everything we've done in trigonometry this year. Yeah, I didn't. But that's the fundamental, okay? And here's your fundamental connection between a unit circle and triangles in the context of this plat problem. We could use the unit circle estimates to refine our estimates of these proportionalities, and then we could use these ratios, proportionalities, to correct our calculations of the areas of the plat and come up with something that's probably quite accurate. Don't know if we would actually be able to determine down to the nearest foot whether that creek that runs along the back here is on the property or not, but we could get pretty close. So there are connections, and of course these sine and cosine functions that you get in trigonometry is a whole different class of functions with a whole different set of properties. So we have trig functions to add to what we've done with power functions and exponential functions. If we throw those together with inverse functions, which we haven't talked much about, but you get the inverse of one of these functions if you just switch the x and y coordinates of every point, basically switch the axes and see what you've got. You have a pretty good catalog of the functions that we study in pre-calculus or analysis and in a calculus sequence all the way up through differential equations. You're going to get most of these would constitute most of the functions. Now, the function picture gets somewhat more complicated when you start combining these. What do you do if you have a power function of an exponential function, or an exponential function of a trigonometric function? These things arise, and that's where things start to get somewhat complicated, but the rules are really fairly simple. If we learn to follow the rules and base what we do on rules, in addition to reflex, we come up with a much more powerful understanding of functions and the things that almost everybody studies up through their first college level math courses, up through their college level math sequence. Now, people that go into mathematics and physics and other scientific disciplines that are more highly mathematical go much beyond a basic calculus course, but this is really a good basis for understanding the things that we deal with in calculus and through the curriculum that goes through analysis and pre-calculus and so forth. So it's an important picture. I'm going to do more videos to extend what we know a little bit, and I certainly hope people will at least take a look at them every once in a while. And also at Khan Academy, there are lots of videos out there. My videos are going to be aimed at looking a little more deeply. Doesn't mean they're going to go deeper than Khan's videos. Khan's videos go quite deep, but I'm going to address that whole process of reflex versus rules and understanding and proof and things of that nature.